It is Professor Hanna from Penn State. Chad has been part of the gravitational wave community for many, many years. If you've ever been down at Louisiana State University, they have two things that really distinguish that campus from every other campus. One is it's the only campus I know on where you can go and take a tiger in real life. And two, if you go down to the basement of the physics building, you'll see the very first gravitational wave detector, which is thankfully not what they're actually using today, despite the fact that it might have higher sensitivity than the carbons. This kind of observer it is also a place where one of the few LIGO detectors currently is based. And starting as a grad student there, Chad worked on compact binaries, going on to a postdoc at Caltech, and then the Gravitational Institute of Theoretical Physics before moving to Penn State. But throughout that entire time, she's been a leader in gravitational wave physics and cosmology, and will tell us all about his work. Yeah.
Hi, good afternoon, everyone. Can you hear me?
Oh, yeah.
Oh, good. 20 years. Yeah, more than 20 years at this point, I think, is how long I've been doing this. First of all, I want to thank you all for inviting me. I've only been here a short while, but I had a wonderful meeting with students and postdocs this morning. Looking really very forward to this talk. I've prepared a pretty general talk, kind of colloquium level, and I think that that's going to be good based on some of my interactions this morning so far. Happy to take questions at any point. Please interrupt, and if I need to adjust for time, I will. Okay, so most of what we've learned about the universe throughout history has been through what we could actually observe with our eyes. And even to this day, a lot of what we learned about the universe comes through, studying the universe through optical electromagnetic radiation. But within the last, 100 or so years, we've obviously extended that to the whole spectrum of electromagnetic emission and particles such as neutrinos and cosmic rays and other things. But we now know about the universe is, of course, that most of what's out there in terms of matter and energy is actually dark. It does not emit electromagnetic radiation. And so I'm here today to tell you basically about one of the ways we have to probe the dark universe through gravitational waves. Gravitational waves are a prediction of the most modern and complete theory of gravity we have, which is Einstein's theory of general relativity, which proposes that gravity is the bending and warping of space and time due to matter and energy. And that bending and warping of space and time affects the motion of objects. And the interplay of those two things results in what we see and observe as gravity. And one of the most one of the most interesting consequences of general relativity that was predicted, more than 100 years ago at this point, is that if you have a dynamic system of objects, say two stars in orbit around one another, they're each individually warping the space and time around them. And in the right circumstances, that warping of space will propagate away from the system, travel across the universe, and can even be observable here on Earth. As certainly some people here know, modeling exactly the gravitational wave signal that one might get from something like this can be very complicated. But by the time that signal arrives here at Earth, by the time that physical effect, I should say, arrives here at Earth, it's pretty well characterized in a simple way. So a gravitational wave will be generally a plane wave that's propagating and stretching and squeezing space in the direction perpendicular to its motion. So if we go back to this system here and imagine that we're sort of above it, or that the system rather is face on very far away through this screen, as that binary orbits, it's stretching and squeezing the space perpendicular to the direction of motion. And the physical effect that we observe with gravitational waves really is a change in distance, a stretching and squeezing of space that we characterize with an amplitude called gravitational wave strain, defined just like mechanical strain. It's a change in length divided by the nominal length of the distance between 2 points without the gravitational wave. To detect gravitational waves from this change of space, change of distances, we use laser interferometry. And the idea is that we send a laser beam into a beam splitter. It goes down 2 orthogonal arms, bounces off mirrors at the end, comes back, and if it's traveled the same path length, when it recombines, it will destructively interfere and produce no light on this photodetector. But a passing gravitational wave is going to stretch and squeeze space separately, differentially in each of the arms. And as it does that, some small amount of constructive interference will occur in a time-dependent way that we can measure on this photodiode. So by taking this measurement and doing some careful calibration, that's how we infer the passing gravitational wave strain. You wouldn't need to look to the stars to produce gravitational waves. You could take any 2 masses and put them in some sort of circular orbit. And just for kicks, to sort of give people a sense of what this is like, if we imagine taking 2 1-kilogram masses, so a little lighter than a bowling ball, spinning them with a 1-meter radius, and somehow we were able to engineer a material and a device that could get that going at a kilohertz, put that on our lab table and then ask how much power is emitted in gravitational waves, it would be 10 to the minus 30 watts. And for scale, the cell phone that's basically in everybody's pocket, or the radio transmitter that's using, that I have on my pocket here that's making this microphone work, they're all about a watt. So about 10 to the minus 30 is 30 orders of magnitude smaller in power than sort of the typical radio transmitters we might have in our life. The Earth-Sun system is a convenient nearby binary producing some gravitational waves. And there's at least a sort of macroscopic amount of power, 200 watts from the Earth-Sun system. The Alpha Centauri, which is the closest binary star system, produces 7 megawatts, which also sounds kind of big, but it's still pretty small on a cosmological scale. For reference, the biggest radio transmitters on Earth are about 1 megawatt, give or take. So still quite small. But this is just all to kind of set a scale relative to what we're familiar with electromagnetic radiation. But in actual fact, what we observe is this stretching and squeezing of space. And so if we were to take perhaps the most promising of these examples, Alpha Centauri's strain, and look at what that would be here at Earth, we expect that the Alpha Centauri binary is stretching and squeezing Earth by about a few parts in 10 to the 23. And to give, again, some sort of sense of scale, that would be equivalent to taking the entire Milky Way galaxy and nudging it, squeezing it by just 1 inch. So it's an extremely small physical effect that we're trying to measure here with gravitational waves. And hopefully this sets the scene of when you all think, well, why did it take you 100 years to figure out this whole gravitational wave thing? It's clearly an extremely challenging problem. And even though gravitational waves were first theorized in 2016, it took all the way to 2015, 100 years later, for this direct measurement to be actually realized. And the reason it took so long is many-fold. Certainly, technologically, lasers didn't, of course, exist in 2015 or in 1915, right? Technologically, we had to make many advances to actually be able to design precision measurement devices capable of this. Another story which is extremely important is, and I'll motivate this later, we actually needed that compact objects even exist, things like black holes and neutron stars, which was certainly not a given in 2015, or 1915. We didn't even understand the atom at that point. And so we really need not only theory, but observation, sort of building a community looking optimistically for compact objects like neutron stars and black holes. And of course, we needed a host of advances in modeling and in data analysis methods and computation. Okay, so the current state of the art with gravitational wave detections look like this. And with some luck in our lifetime, this will get even better with new instruments. At the moment, we have 4 ground-based gravitational wave observatories at a similar scale. So in the US, we have the 2 LIGO observatories, one of them in Livingston, Louisiana, which is outside of, kind of in between Baton Rouge and New Orleans. And the other one is in a DOE site in Washington State, Hanford, Washington. We partner with an observatory in Italy called Virgo, and most recently with an underground observatory in Japan called Kagra. And each of these have have kilometer scale long arms. So LIGO has 4 kilometer long arms, and then each of Virgo and Cagra have 3 kilometer long arms. And this is pretty critical for this story because since we're measuring gravitational wave strain, if we make the arms of the observatories as long as possible, we can get away with measuring larger actual displacements and still maintain a similar strain sensitivity. There are limits to what we can do even with these interferometers on Earth. So this is called as sort of a misnomer called a strain amplitude spectral density plot. What you should get from this is the characteristic level of noise in terms of strain at a given frequency. So you can see on this x-axis we have hertz. This is about the bandwidth of the human ear, especially when you're old like me. Some of you young people can hear higher than this, but roughly speaking, this is basically what humans hear. So much lower frequency than what any other astronomer is going to talk about, even you radio astronomers that are in the audience. But you can see that even here there are limits. At very high frequency, we can't make observations, and at very low frequencies, we can't make observations. And although it may be possible to make some progress here, it's unlikely there probably are many sources at very, very high frequencies. But down here at low frequencies, it's nearly impossible. And the reason is it turns out that the Earth is just constantly moving at about a decihertz just from seismic motion. So the ground is sort of shaking at a micrometer kind of all of the time, which makes it extremely challenging to observe down here. And that's going to be an important part of some of the story that I'll tell a little bit later on. Okay, so I think probably everyone in the room is, as familiar or potentially more familiar than I am with stellar evolution. But we know that when stars grow old and run out of fuel, they end up with some final state depending on their mass. Lower mass stars will end up as white dwarfs. More massive stars may end up as neutron stars, and if they're very massive, they'll end up as black holes. All of these we sort of view as final states. Neutron stars are about the most compact thing that we're aware of. They are sort of just bigger than the black hole event horizon in some sense. They're an extremely dense form of matter. Black holes, of course, have collapsed entirely to where all of the matter is now within an event horizon that nothing can escape from. Someone asked me earlier a great question about will LIGO ever be able to observe white dwarfs? And the answer to that is unfortunately probably not. And here I have, and situations even considerably worse, of course, for main sequence stars. And to give you some sort of physical intuition of this, I have a really terrible physics example, which is if you were to model stars as uniform density rigid objects, which is clearly how they work, and then put these two things in some sort of Keplerian orbit under gravity and allow them to get as close as possible without touching. If you do that problem, you can figure out the frequency, and of course it depends on the density and the size of these objects, and it turns out to be a really simple formula. The frequency of gravitational waves up to factors of unity will go like the square root of g times rho, where rho is the density. So if you want to get gravitational waves that are in the LIGO band, let's pick a kilohertz optimistically. It's kind of higher frequency than we need, but at a kilohertz. What you conclude is that to do that with, again, that sort of simple physical argument, you need to have matter that's at nuclear density. And so this is why, it's been extremely challenging to have, gravitational wave sources that are relevant for LIGO, because we really need special sources. We don't have any sensitivity to main sequence star, white dwarfs, or anything less compact than a neutron star, or at least not much less compact than a neutron star. Decades and decades of modeling went into understanding how gravitational wave signals should look. So here I've taken an excerpt from a fairly famous paper. This plot is showing the x-axis is time, the y-axis is strain. It's showing this gravitational wave signal from a compact binary merger. And in this situation, the sort of physics for something that's undergone a long evolution is all reasonably similar. There are sort of 3 phases for a compact binary, one of neutron stars or black holes evolving. There was a very long phase at which the two objects are just in an orbit that's quasi-circular that goes on for a very long time. and is slowly emitting gravitational waves at some roughly constant power, losing energy. But over time, that energy, of course, is affecting the binding energy of the system, and the orbit's actually shrinking. And as the orbit shrinks, the gravitational wave emission goes up, and this becomes a runaway reaction that eventually causes the system to merge, form some final object, and then settle down to a state that no longer emits gravitational waves. We understand the first part pretty accurately through approximations to general relativity. This first part produces a very specific time frequency evolution that for the most part only really depends on this special combination of the masses called the Chert mass. It's the product of the two masses in the binary to the 3/5 power divided by their sum to the 1/5 power. This part here, this will date me, Gotham. When I started in this field, we didn't know that. That was news. So this part here, the merger, really took significant advances in numerical relativity and, of course, supercomputing, not unlike the type you all do here, before we had any idea what this part looked like. This is the sort of most nonlinear and difficult to solve portions of Einstein's equations for these systems. And it seems like yesterday to me, but I think the first complete orbits were published in 2006. So it's been a little while now, but this is a very, in some sense, modern thing in our field. In this last phase, we also understand parts of through numerical relativity, but people had also developed other perturbation methods on spacetimes of black holes. Yeah, Chuck?
I just want to get a feel for them, because I'm not one of you folks, okay?
Yeah.
What is the magnitude difference between the part where it's in the process of merging versus that actual merger event? I'm just trying to understand what that y-axis scale is there.
It's a linear scale.
It's a linear scale?
It is.
Okay, so it's about what? Twice as large? 10 times what?
Yeah, although, this is only showing, I've not put actual time labels on here, but for the particular event that this, for a LIGO event, this may be, just a fraction of a second.
Oh, wow.
Yeah,
All right.
yeah. So it's a very short time scale. The lighter events may last minutes, but we typically, even though we sort of do observe all three phases, we're really observing it very, very late in its evolution. It might have existed for hundreds of millions, billions of years prior.
Thanks. Appreciate it.
This always confuses me a lot. Does that fraction of a second of their merger, is that like how fast it's happening in their rest frame? Or is it something that takes millions of years?
No. It happens quickly, although there are, of course, time dilation effects to worry about. No, the key thing is, let's see. The key thing is this. So systems will in general spend a very, very long, binaries that might have been formed, right after the first stars were made and collapsed and whatever, could be undergoing gravitational wave merger for the age of the universe effectively. And if they're too far apart, which most of them are, they'll continue to, not merge for a long, long time. But what we're sensitive to with LIGO is only frequencies above, in round numbers, about 10 hertz. So for the mass ranges that we're considering, which is roughly the mass of the sun or a little more, this really corresponds to the last several minutes of binary mergers at best, because they have to have gotten extremely close together before the frequency is sufficiently high. Because remember that what this 10 hertz means is that these things are orbiting each other, 5 times per second, half of this. If you add something that is not a black hole into one of these systems, for example, a neutron star, if we consider the neutron star a black hole system, generally speaking, especially these initial phases of in-spiral, the initial phase of in-spiral, will proceed almost exactly as it would for two black hole sources. It's only when the neutron star gets somewhat close to the black hole that sort of differences emerge. The neutron star being an object that has actual matter can be tidally deformed. Think the oceans on the Earth. And so you can pull the neutron star and sort of turn it into an egg shape. That has two consequences. First, that deformation of the neutron star does slightly alter the evolution of the system. It drives it to merger a little faster, changes the gravitational waveform. That turns out to be a pretty challenging thing to measure, but a very important thing for us to become better at measuring, and something that will happen in time. And the other thing, that's perhaps exciting for at least some people in the room is, given the right circumstances, the tidal deformation may get so strong that it actually pulls the neutron star apart. And if that's the case, within almost all reasonable expectations, you're going to end up with some sort of electromagnetic or particle outburst as this disrupted neutron star is forming an accretion disk around the black hole. Now, in order for that neutron star to get close enough and tidally disrupt, these systems are so cool to me because they involve the confluence of standard model physics beyond nuclear density, so neutron stars. They involve general relativity sort of at its cleanest, like ideas at least from general relativity sort of at its cleanest form, understanding the geometry around a spinning black hole, a Kerr black hole. And all of them come together to produce a sort of set of observable consequences that if we're able to actually, over time learn about them, we have the ability to learn so much about systems that have not only this, the most extreme matter, but also the most extreme gravity present at the same time. To get this neutron star to disrupt, generally one of two things has to be true. You have to have mass ratios of the two objects that are sort of comparable. So if the neutron star is too small compared to the black hole, it sort of just falls right in. And you also have to have the right spin on the black hole. It turns out if the black hole is spinning and the orbits are retrograde, that it also can more easily fall in. So there's sort of this interesting bit of physics that goes into whether or not this thing produces a tidal disruption. And in my opinion, this is a very interesting area for us to map out in the next few years. Two neutron stars, the outcome is, I think, much more certain. There's no black hole for the neutron star to fall into. So here you have two giant, again, things that have regions that are above nuclear density, blobs of matter, orbiting one another at close to the speed of light and then smashing together. It's kind of the biggest particle accelerator you could imagine. Understandably, this produces a lot of electromagnetic emission. It's kind of difficult to imagine that won't be the case. And long before this was observed directly, folks had modeled quite completely the picture that this would produce. The two neutron stars merge together. In most circumstances, they form a black hole, probably pretty rapidly. And there will be some accretion disk and some, obviously there's a lot of angular momentum, can drive, for example, a gamma ray burst. And there'll also be some ejecta that comes out of the system. And again, this matter is extremely hot, extremely dense. And as it goes off into the universe, it cools and emits a host of electromagnetic radiation all the way from UV or higher down to radio. Although, different people in the community have different priorities. Fortunately, throughout advanced LIGO's era, there has been a large fraction of the LIGO community that has looked to try to produce gravitational wave discoveries in real time to enable the possibility for multi-messenger astrophysics. I'm assuming that's a term many people know. The idea is to observe a single astrophysical phenomena through different messengers. And here messengers really are, vastly different things. If you say UV and IR, maybe that's multi-wavelength, but here I'm talking about gravitational waves and neutrinos, or gamma rays and gravitational waves, things that are really talking about even different fundamental forces that are involved. And with gravitational waves, especially for systems like this, and hopefully also someday for neutron star black hole systems, there's a real opportunity because we know it's going to happen. We actually observe the neutron star merger even in this early phase. And so we know something's about to happen. And so we have an opportunity, if we're fast enough, to let people know that a merger has either just happened or maybe is about to happen, But we know very precisely when these two objects have smashed together, and far less precisely where they have come from. But hopefully that's something that can change. But nevertheless, we have a fairly large infrastructure that is in real time gathering LIGO strain data, sending it to data centers all over the world, and searching for millions of different gravitational wave models in parallel in real time. And when discoveries are made through an automated process, initial candidates will be shared with the community publicly in the hope that counterparts can be found. Gravitational wave, yes, please.
How long can you store that information if you want to retroactively look for a merger?
Oh, we store the data indefinitely. The gravitational wave strain data is embarrassing. Remember how I said it's embarrassing in the sense of like big data? I'll give you more in a second. You're gonna be like, what are you even here for, man? This is NCSA. Did you not read the sign out there? Remember how I said this is audio frequency? Mm-hmm. Yeah, so like streaming LIGO data is like streaming a CD. Oh. Like a compact disc for those of you who are too young. Like an MP3, I don't know, whatever. Spotify. It's like you could easily broadcast it over Spotify, no problem. So the strain data is trivial. We store it indefinitely. Yeah. There's a lot of auxiliary data that's also important for understanding the LIGO system. At one point that used to be big data, but nowadays also not really big data. We store that indefinitely too. Yeah. Petabyte a year, a couple petabytes a year. For the full auxiliary data, it's nothing. We're actually a data amplifier. We take that kilohertz data and then run it through a bunch of filters to turn it into gigahertz data, which we then look for. I mean, that's our representation of the really high fidelity signals. So it actually involves a bizarre data amplification. This is now wrong, actually. I forgot to update this slide. It's 9 years ago at this point. The initial gravitational wave discovery, after many, many decades of work, leading up to LIGO, that is clearly related to LIGO, came in fall of 2015, and we were extremely lucky. We found a binary black hole system that was so loud that you could actually observe it more or less in the raw strain data. This data has been minimally processed, and you can see this wonderful raw data that shows an increase in both amplitude as the system evolves, as well as frequency, with each one of these peaks getting closer together. And for reference, so this system turned out to come from two 30 solar mass black holes about 1 billion light years away. The peak strain is 10 to the minus 21. So LIGO delivered on these extraordinary promises of being able to make extremely precise distance measurements. Going back to the Milky Way comparison, this is a little more optimistic than the Alpha Centauri binary. This strain corresponds to squeezing and stretching the Milky Way by my height. So clearly much easier than 1 inch. And so far, this signal and the other ones we've observed have been completely consistent with general relativity. Many of you have probably seen this, but this is sped up by a factor of many. This whole thing would have happened, in a short amount of time, like a fraction of a second. But here's a sophisticated simulation where we were able to actually back out the general relativistic parameters. I mean, not me, the people that made the simulation, the SSX collaboration, to show kind of what this would have looked like had you been there. And it's good that we have such sophisticated models from general relativity, because this is how we learn so much about the system. How do you turn this little wiggles into some estimate of the masses and the spins? And because we're able to solve the two-body problem in general relativity, we can solve for every possible model within a vast parameter space of masses and spins, and then fit those models to the data. Certainly to come up with the best estimate, but also to come up with uncertainties in the form of posterior distributions for binary parameters such as masses and spins. I would say the next most famous gravitational wave came in 2017, where instead of two black holes, we for the first time measured gravitational waves from two neutron stars that merged together. And of course, when they did, produced a gamma ray burst and then subsequently a host of electromagnetic emission over the coming days, weeks, months, and years. This initial detection of the event known as GW17817 was, the signal first arrived at Earth and was detected in gravitational waves. This is a time frequency map. This bright line that increases in this plot is showing the frequency evolution of the neutron star. Here is approximately when the neutron stars merged together. And about 2 seconds later, there was a gamma ray burst detected by Fermian integral. And over the coming hours, about 11 hours later, and then over the coming days, weeks, months, and years, eventually observations were made essentially across the entire electromagnetic spectrum from this single event. And it's probably a gross oversimplification, but in the end, the sort of picture unfolded not so unlike what folks had expected, definitely leaving some open questions. One of the unfortunate things from this event is we did not have precise sky localization early on. It was sort of a lot of just really unfortunate things from many communities, just bad luck, essentially. And we did not get a precise location early, so we don't know anything about the electromagnetic emission other than gamma rays before about 11 hours. So the hope is that we will get another one of these sooner rather than later and start to fill in some of the missing pieces. People had asked, some of the students asked great questions earlier about the balance of physics versus astronomy in my field. And I gave the anecdote that when I was hired at Penn State, I was hired into the physics department because we did not yet have any gravitational wave observations. We were firmly a fundamental physics experiment. We didn't even prove that gravitational waves had existed until that point. It is certainly the case, though, that after that initial detection, a change occurred where we are now obviously moving more day by day to being an astronomical observatory. But there is still a lot of fundamental physics that can come out of this experiment. This GW17817, just to give a very simple example, under what I would argue are entirely reasonable assumptions regarding the relationship between the merger and the gamma ray burst, the fact that those things were observed just 2 seconds apart here on Earth places extremely tight bounds on the relative speed of gravitational waves and light, which is, again, something that's not entirely obvious. It's what GR predicts, but if GR is wrong, that may not be true. This simple relationship between the speed of gravity and the speed of light improved by, 15 orders of magnitude on previous bounds on that quantity, just from this one observation. We were able to also measure the expansion rate of the universe, the Hubble constant. We have a accurate but imprecise estimate. The single event, given that we were able to localize to a host and also get the luminosity distance from the gravitational wave signal, allowed for an independent measure of H0, which this plot is quite old. I took the original one. It basically spans the space of known values of H0, but does not help us yet resolve any Hubble tension, although perhaps maybe someday if someone doesn't beat us to it. Since then, we've had an opportunity to detect about 100 gravitational waves, detect and publish, fully vet about 100 gravitational waves of all shapes and sizes. Hopefully this will play. Oops. There we go. But largely, it's been mostly binary black holes. Now, we have some sort of counterexamples of that, which I'll talk about here in a moment. We learn about the universe in two ways with gravitational wave observations, sort of two extremes of the same thing. Obviously, there are single individual events which advance knowledge. 17817 is certainly one of those cases. The neutron star merger advanced knowledge in many areas of physics and astronomy. However, we also advance knowledge simply by taking a large statistics sample of even relatively individually boring binary black hole mergers. And so I'll try to motivate both those things. First, just some very brief words about the population of binary black holes. When you have a few, you can't say much. When you have 10, you can say maybe a little. But even with 100, which is the most recent set of events that we've published, some interesting things are emerging. So if you look at the raw histogrammed data of gravitational wave detections in this chirp mass quantity, which is the thing I introduced earlier, the reason why that's a good one is because it's well measured, and so it's just a nice variable to include, in looking at raw data. Already there are some sort of features that emerge from this. And if you try to infer then the universe's merger rate as a function of this parameter chirp mass, what we're now pretty confidently seeing is a spectrum in this quantity and in other quantities too that's not featureless. So it's not just a simple power law or some simple Gaussian, et cetera. For reasons which I think will only unfold over time, there are preferred masses of compact binary mergers that appear to be produced in the universe. And this is something that we're only going to be at better and better estimates of even in the next year or two. We should be able to make substantial progress on this problem. Please.
Are those the masses before the merger, or masses the sum after the merger?
That's a very good question. I think this is the chirp mass of the binary, so it's not the total mass post merger. If that's your question, it's the chirp mass of the binary.
So, but then how does this here? Are those the same? So it's the mass of each individual black hole, not.
No, it's the chirp mass of the binary, which is m1 times m2 to the 3/5. Yeah.
Okay, that's how I remember.
But it turns out to be a very accurately measured quantity, which is sort of nice for looking at raw histogram. Yes, please. Sure.
All right. So I've seen plots. So this distribution also needs to be probably modeled by the detection function of your detector, right? Of LIGO.
Of course.
Because I know there's some plots that I'm not familiar with that I don't remember by heart, in which you can plot the chirp mass as a function of frequency for like LISA versus LIGO. And those are different, right? They live in different, they overlap, but also they detect different things. So what I was wondering, if maybe you can tell us, what are the regions for which we wouldn't be detecting objects because of the...
Great question. Yeah, so that's a great question. And this plot here is really just the observed stuff. This is the thing you're worried about, has tons of selection effects. This plot makes an attempt to pull out all of the selection effects and answer the question, what is in the universe? So the quantity on this axis is differential merger rate. It's times chirp mass to make the plot easier to interpret, but it's differential merger rate that we infer in the universe by an attempt to address exactly what you talk about, which is all the selection effects. We could spend an hour talking about how we do that, but I think the simple answer is a lot of Monte Carlos. So a lot of simulations go into this. Yeah. Great question. Please.
And clearly, like also in the universe, on the x-axis, that thing keeps going and going, but we have no idea of that section of the universe, which is like supermassive black holes, right?
Great, thank you. Yeah, thank you. I was gonna say that too, and I'd forgotten by the time I answered the first part. Yes, so this clearly only spans a region that is actually detectable. And again, if we go back to this, LIGO frequency plot, the relevant physics here is, does it merge before this sensitivity band? So if you get too heavy above, it's a spin-dependent statement, but above a few hundred or at most 1,000 solar masses for the binary mass, even in the most extreme examples, above that, the merger occurs below 10 hertz. So LIGO just simply cannot see it for the same reason it can't see white dwarfs. The lower mass bound is a lot trickier. For that, there's no reason why LIGO couldn't observe a chirp mass of 0.0001 if it existed. We have a lower sensitivity to those objects, but, and this is a personal pet project of mine, certainly looking below a solar mass is a wide open area for LIGO where we're really pretty uniquely positioned to discover things there, because we still have a reasonable, extragalactic, like beyond the Virgo cluster kind of reach to such systems. But they'd be good gravitational wave emitters if they exist. We do those searches, but they don't typically get folded into our full catalogs because they're obviously more speculative in terms of astrophysics. Yeah. All right. So this, I guess the final remark on this is, and you'll see in a moment, we're going to triple the number of gravitational wave detections pretty soon. And so we will have a much better understanding of, the reality of many of these wiggles in the coming months and years. I won't talk too much about this because we're kind of low on time. So I also mentioned that we learn about the universe not just through these populations, but through individual events. So I've kind of hand-selected a few individual events that I think are kind of my favorites, and they sort of come together to tell a little bit of a story about what I'm looking forward to in the future. GW 1904-25 is an event from 2019, and apologies, these are kind of old, but I'm building up to a little bit of a story here. This is largely regarded as LIGO's second binary neutron star merger. Now, the main problem with the statement is we have no idea if it's a binary neutron star merger. And the reason why we have no, exactly, right? We have no idea if it's a binary neutron star merger. I can tell you it's a gravitational wave. I can tell you it's from compact objects that are at least as compact as neutron stars. But I can't tell you that it's not two black holes. I can't tell you that it's not one black hole and one neutron star. And the reason I can't tell you that is because we did not measure any tidal deformation. So we cannot say matter is present from the gravitational waves alone. And there was no electromagnetic counterpart, which would have been probably a dead giveaway if there was matter in the system. Now, the lack of electromagnetic counterpart does not say that they were black holes. This is an extremely challenging system. The sky area was like thousands of square degrees. So it was hopeless for sure. But I want to point out that there's some odd things here, right? Well, odd maybe, depending on your perspective. If this is a double neutron star system, it is certainly different than the rest of the galactic population, and it's different than GW 17817. And the simplest way to see that difference is, here is the histogram of an admittedly small number of galactic binary neutron stars, which have a pretty tight distribution in total mass. Here is the posterior distribution in total mass for this event. They differ quite a bit. Now, neither of the masses involved in this are inconsistent with neutron star masses on their own, but they're also not inconsistent with black hole masses either, so we're just really not sure. The second event that's of interest is 1908-14, and this turned out to be one of the loudest gravitational wave signals to date. It's no longer the loudest, but it's still extremely loud. I forget the SNR, 30 something, it's quite loud. And what was cool about this event is because of how loud it was, and some other properties of it, we were able to measure the mass posteriors very accurately. So this event, in terms of our best guess of the masses in M1 and M2 space and solar masses, shows that the secondary mass is very tightly constrained to be about 2.6 solar masses. This is somewhat interesting because historically, and less so now because I realize there are other observations, but historically this sort of represents an area where there was a known dearth of observations, often called the lower mass gap or the observational mass gap. And this puts the secondary component of the system firmly in this region of 2 to 5 solar masses, which previously had not really been filled in at all. GW 2105 and 2115 are often regarded as the first probable NSBHs. Again, I want to say we have no idea. I'm sure that they are gravitational waves. They're nice, loud, obvious signals, especially one of them is extremely loud. But I can't tell you for sure if there are any neutron stars involved at all. Now, I will tell you that at least for one of them, it kind of has this, very nice secondary that falls right around the mass you'd expect for a neutron star. But again, we're just not sure. We were not able to measure any of the tidal deformation, did not find any electromagnetic counterparts, but we have these two events that if you sort of If your prior is anything less than 2 solar masses, it's a neutron star, then these events are for you. And if it's not, then I'm not sure what to tell you. They could still be black holes. The most recent discovery, sort of in this interesting space of ambiguity between neutron stars and black holes, is GW 230529. This is the first event to be published from our current observing run, which is ongoing. So it's now a little bit old, but still feels pretty new to us. This GW 230529 is a very low mass system, but the primary mass now is sort of firmly within, again, this observational or lower mass gap, with a best estimate of about 3.6 solar masses. You will not be surprised to hear the next things out of my mouth. We, of course, do not know if these are neutron stars or not. They could be black holes. They could both be neutron stars. That one's tricky. Yeah, I know, I see some frowny faces. Tell me how this is true. You're thinking. So if you believe neutron stars can be up to 2 solar masses, and you can get them spinning up to 0.4 of spin, and the spins are anti-aligned with the orbital angular momentum, it turns out, yes, these could in fact be 2 neutron stars. I don't believe that that's the case, but I'm just trying to drive home. We only learn so much from the data, and a lot of what else goes into these interpretations comes from our prior belief of what's out there in the universe. Yes?
On the previous plot, can you comment on the degeneracy direction between the masses? Why is the larger mass so much better constrained than the M1 is much better constrained, it looks like?
Do you mean, I guess...
the posteriors in the M1, M2 plane have a particular degeneracy direction. Can you comment on why that is?
Yes. Okay, yes. This here?
Yeah.
That is chirp mass. That is a line of constant chirp mass.
That's just the thing you actually constrain. Okay, I see.
And with sufficient SNR, you can get more out of it. But at low SNR especially, that's really the thing you're measuring. And so you're seeing that relationship.
Okay, gotcha.
Thank you for asking that question. Please.
Can I ask another one? So in the previous one, you're actually not reporting the distance, but I know you probably have the distance regardless of there's a counterpart, right? So only in the last one it was like 0.04.
Yeah, I just didn't put it in the slides. I can look up what it is for you. Yeah.
And then you also reported before that the one that was the loudest. I don't know if I put that there or not either. But I can answer all of these questions if you right. So as a curiosity, so it's the loudest because it has like the highest amplitude in the chirping, right?
Yeah, specifically the highest signal to noise ratio, which is an integral.
Okay.
But roughly speaking,
how is that related to distance? And the other thing I wanted to ask is like from all of the sample, now you have like over 100, right? They're all within a certain range. So these are not things that are ratio of 1.5, right? So they're all like in our backyard, in general. The black, the mergers that you're seeing, all of the gravitational wave events that you're observing from your modeling,
yes,
they're here. They're not in the distant universe.
No,
correct.
No, that's right. Especially for these lighter ones. Mm-hmm. Basically everything I've shown you in the past few slides have been redshift 0.1 or less.
Correct. So, and I guess what I'm heading is out of the lack of electromagnetic counterpart is not because it's not because they're like very faint. Well, it's not because they would be undetectable by our technology. Is that most likely they were not there? That's actually what I...
Yeah, that's a great question. I don't think I would go that far, and I will gladly defer to others in the room who do this side of things for a living. My take on this is, in many cases, well, especially, the simple answer is actually this one. I don't remember the distance. I think it was about 200 megaparsecs. Yeah, here, sure. But the sky localization was thousands of square degrees. And so there was just no good place to tell people to look. So, when you're trying to find a fading signal, 200 megaparsecs, my understanding, is kind of at the edge of maybe kilonova. I don't know where people really think that line is, but people in the room certainly know. I'm sure Gotham knows. It's a little challenging at that distance, and there's no sky localization. So for this event, I think this event could literally have had a great counterpart that would have been detected. It could have just not been found in time. People tried very hard for this event, but I I would not say that we can rule out the fact that it has a neutron star based on the lack of observations. Yeah, the others I'd have to remember some of the distances and things. But they're all local universe less than redshift 0.1. We can see the heavy black holes now to redshift of order unity. Yeah. So this event has, what am I doing on time? Oh, good. All right. I will make that time. This event fills in this sort of crowd of interesting lighter events for LIGO. So if we look at the M1 and M2 plane, now with all of the events that we know that are sort of not heavy black holes, we have now a sprinkling of objects ranging from the lightest, which is the GW170817, up to the heaviest, which is the one we talked about a couple slides ago, 190814. And if you squint, I sort of especially believe that these are probably neutron stars. I'm a little less certain about this one, but it could still be a neutron star, certainly. This one seems almost certainly not a neutron star. But we're now definitely firmly in a regime where we have reached a sensitivity where we can really start to fill in this plane. And I think this particular last event is exciting, this GW230529, because just that single event has dramatically improved the prospect for small mass ratio events, meaning, or I should say, approximately equal mass NSBHs. We basically, this is a somewhat technical plot, but again, going back to the inferred merger rate in the universe versus now just the black hole mass. Previously, we'd kind of thought that there aren't many small black hole NSBHs based on what we had seen. Just a single event definitely improves the prospects here. And why that's important is because this is exactly the scenario under which we might expect electromagnetic counterparts. So this one event has improved prospects for MMA, for NSBH by quite a bit, although we clearly haven't seen a counterpart for this event, but it is now a much more likely thing and kind of exciting for the rest of the observing run. And again, for the reasons that I mentioned before, which I won't go back over given the time. All right, so to recap, I can now pretty firmly tell you we've got plenty of objects that are in this lower mass gap. It remains to be seen if it's, if there is a dearth still there or not, but we've been very steadily filling in objects in a region which had not been well populated prior to LIGO, although now is also becoming populated via other observations. We know we've detected at least one neutron star, and that's it. 17817 could in principle have also been an SBH. Probably not, but could have been. So we can tell you from LIGO that we've detected one neutron star, but that's about the best we can do. Everything else, it's still open. It seems likely that what's leading to binary black holes is probably like the distribution that we observe is potentially some interesting things, maybe more than one formation mechanism. We're going to learn a lot more about the binary black hole mass spectrum in the coming years. And this sort of population of lighter gravitational wave objects, in my opinion, are really interesting. They're starting to fill in this M1, M2 plane and all over the place. We're going to start to really probe the boundary between neutron stars and black holes, the boundary between things that are EM bright and EM dark, only through continued rigorous combination MMA analyses, which I'm looking forward to. Our current run 04 is ongoing. As of last night, we have 152 significant detection candidates. That should be framed with the context of the previous 100 from all the observing runs combined. We're on track to probably hit, it's a little hard to say, we've had a few slumps lately, but we could get up to 250 by the time the run's done, which means that we'll more than triple the catalog of known events, increasing the statistics on many things. Of course, what I'm really hoping for is that we get lucky and there's another multi-messenger event before the end of the run. Poisson statistics are this way, right? Like, there could be 0 for a year and there could be 4 in March. So let's hope for the 4 in March. Those of you who want to follow along at home can visit gracedb.ligo.org. You can also keep track of detector status, which right now isn't great, I'm not going to lie. By looking at online.igwin.org, it gives you a real-time and historical view of how things are going over the run. To frame this in terms of the future, we are here in LIGO's 04. We will end midway through 2025. The proposed end date's June 9th. There will be about a 2-year break where we have another run called 05 with the hope of a substantial increase in sensitivity. And then beyond that, I've not tried to put in a plot or say, but I can speculate a little bit. Another observatory called LIGO India will be coming online right around 2030. It'll take a while for it to get up to sensitivity, but with some luck, the 2030s ought to be a good decade for multi-messenger astronomy with good sky localization brought by at least 3 LIGO grade instruments. So I will end there and also say, here's my group, and they've been the ones doing all of the work. Thank you. There were already a lot of questions, but if you have any more, please, yes.
Can you comment on the spin of the compact objects? You're talking about the parameters M1 versus M2.
Yes.
How about the spins of the neutron stars and also for the black holes?
Yeah, great question, and I kind of glossed over all of that. I only had one slide on it anyway. Except for rare cases where you get something that's kind of loud and has the right parameters, measuring individual spins is pretty hard. We measure a combination of the spin called what's called chi-effective. It's the spin component projected onto the orbit angular momentum. So if the black hole, or if the orbit angular momentum is up, you look at the spin components individually projected onto that, which we'll just call the z-spin. We measure a parameter which is the mass times that projection added for the 2 binaries divided by the total mass. So it's this sort of mass-weighted angular momentum projected component. That's the best measurement for spin. Now, it's not telling you the spins of the individual objects because of all the things I just said. It's giving you one slice into that. That being said, this is the last published distribution of this quantity, which is largely centered around 0.
This is for black holes, or is it?
For the binary, for the chi-effective, it's a parameter that combines both spins. We get the best estimate. Maybe you're asking is it for black holes or neutron stars? For black holes, yeah, for black holes, which is most of our sample. We have nearly 100 black holes and only a few that are neutron stars. Yeah, for neutron stars, we basically don't measure the spin at all. We just can't get the spin out very easily in gravitational waves.
So essentially, the masses can be totally different depending on the spin in the neutron star, let's say, case.
Oh, I see. Yeah. And I should say that whenever we do modeling that tries, like Bayesian inference that tries to put in some sort of priors, the collaboration has been pretty good about looking at low spin priors, high spin priors. I mean, neutron stars can, as you I'm sure are well aware, can spin pretty rapidly before they, before causality is violated or before they fly apart or some weird things like that, right? Like they can spin pretty fast. So we will often in papers provide 2 priors for spin, one which is the smaller old neutron star prior, and then one which is closer to the fastest pulsars. They sometimes change. Like I said, so I mentioned this in a passing, but this one event here, it turns out you can interpret this so this is exactly your question. If you play with the priors, right, you can interpret this as a double neutron star binary, but it involves each neutron star spinning at 0.4, which is fast, and for the spins to be anti-aligned with the orbit, both of which seem, while not impossible, pretty difficult to construct. Yes?
I have a basic question about the relativity aspect of this. Like, is the speed of propagation of these telling us something about like the tautness of space-time? I mean, what is supposed to set that speed or give us a sense of how fast that's supposed to go?
I mean, in GR, it comes out as the speed of light, just like in Maxwell's equations, electromagnetic waves come out as the speed of light.
Really? So like
it's expected in GR that gravitational waves will travel at the speed of light. In other non-GR theories, that can be different, and that's exactly why this measurement was able to rule out a lot of non-GR theories in principle that could have predicted even small differences in that number, but this is so precisely constrained to be the same that there's not a lot of wiggle room left. Yes?
I'm just wondering about sky localization before the 2030s. So early on there were 2 detectors, now there are 4. How good can a good sky localization be now?
Well, what you're asking is how good could it be and how good will it be is what I'm going to answer. And the will it be is unfortunately not great. The reason is that although we have, in principle, 4 detectors, sorry, I'm sure we're now over time, but now that we have 4 detectors, in reality, the Virgo detector did not meet its design goals, so it is considerably less sensitive than LIGO. And CAGRA is not running because they had an earthquake, but even optimistically, it was going to be very insensitive. So it is certainly the case that Virgo is helping, and there have been examples in 04 with sky areas down to order 10 degrees for black holes, unfortunately, not for neutron stars. So it's not that it doesn't help, but you still see most of the events that come out are poorly localized. It's only the rare ones that are kind of loud and in a good place in the sky where we might approach order 10 degrees, but the vast majority are hundreds or thousands still, unfortunately. Yeah.
So part of the issue here is, of course, even with more detectors, they are in pretty much the same latitude band, and you really do need a lot of spread in latitude to get better localization area. Sort of blue sky dreaming, what's the next advance for LIGO? Is it really finding and putting a detector in like the Tibetan plateau or like the Antarctic or something like this, or is it really focusing on lasers and improving the sensitivity of what facilities exist right now?
I think it has to be the latter. The only new facility of the current generation that's planned is LIGO India, and it is going forward. And it does improve the baseline. It does help. With some luck, and especially the strong partnership with LIGO in the US, I think it will deliver. And that, in my opinion, is going to be our best bet for the 2030s. I think we need to go all in. Let's hope for Virgo and CAGRA. Let's all hope that it all becomes amazing. And let's really try to make LIGO plus LIGO India be as good as it can be.
Let's thank John again.
Thanks, everyone.